Alright, hello and welcome back to week 3, everyone. This video is probably going to be a little bit longer than the other two. There's also more material, more stuff going on in this one. I think this one is a bit more fun, more enjoyable than the other two, but this one will also require a bit more attention, just because it's going to be a little bit more profound than the previous two. Okay, so from last time, we were talking primarily about samples and things we can discern from samples. So we said that we had some population and we would draw a vector of values. So we'd maybe have a population of 100 or 1,000 or however many values, and we would draw some number out as a sample, so maybe 50 or something. So maybe we wanted to find an average for the population. We would draw out 50 values and look at the average of those 50 values and then compare it against the average of the population. So the example we used last time was the average number of shots per game by Alexander Ovechkin in the 2018-2019 season. So we started by taking samples of 10 and also samples of size 20, and we wanted to see how well those samples approximated the population average. And what we saw was it wasn't too bad, but there was a fair amount of variation going on. Okay, and we said that we could calculate the sample mean just by summing up all of the values that we get from the population, dividing by the number of samples. And then there was also the sample variance. So the sample variance was we would take the sum of the difference between each value and the sample mean, square that value, and then divide the whole thing by n minus 1. And then I include this notation over here, which is just shorthanding all of this. So what this is saying is we're going to take term x1, add it to x2, add it to x3, all the way up for each j going from 1 to n. So 1, 2, 3, all the way up to n, which is what this value here is doing. And then the same thing going on with this bottom one. So we'd have from j going from 1 to n, we would have xj minus x bar, square that. Then add it to x2 minus x bar, all squared, then add x3 minus x bar all squared, and so on all the way up to xn minus x bar squared. Okay, and then in this one, we want to talk about probability and also random variables. So a random variable, as the textbook defines it, is a probabilistic model for the value of a measurement before the measurement is taken. So the difference in what's going on here is we're looking at something that we haven't observed. When we were looking here with the samples from last time, it was we observed something. We had taken an observation of the shots in a collection of games, and we observed what was going on there. What you do with a random variable is kind of the reverse, is instead of observing what's going to transpire, you kind of look at what could happen when you make an observation. Okay, and then along with a random variable, there's also the idea of a sample space, and this is kind of similar to the population last time, but it is slightly different. So for this, it's the set of all values a random variable could obtain. And we also want to talk about events. Events are just outcomes of the sample space. Okay, so for example, suppose that we are looking at throwing a single die. So we'd let x be our random variable, and e would be the event that the outcome of that throw is going to be 4. Right, so from what we've got here, our random variable is the outcome of the throw on the die. So it could be any of 1, 2, 3, 4, 5, or 6. And that is actually what our sample space is. The sample space is those values 1 through 6. And then the event is anything you could imagine showing up with as a possible outcome. So if you really, really wanted, you could say that your event is going to be the outcome that the face on a regular 6-sided die comes up with an 8. That's completely reasonable to take. It's just something that's not possible because there's no outcome where you throw a single die that has faces 1, 2, 3, 4, 5, or 6, and the face 8 comes up. But if you really wanted, you could say that the outcome where the die comes up as an 8 is an event. Okay, so from this, all of the possible outcomes that we could get are the 1, 2, 3, 4, 5, or 6. So the population mean is just summing up all of the values in the population and then taking the average. So for us, we'd add up 1, 2, 3, 4, 5, and 6, which is 21. We would divide it by 6 and get 3.5. For the population variance, it's similar to the sample variance, but there's one major difference. So as with the population, or with the sample variance, the numerator is going to be the same. We take that sum of squares of each entry minus the population mean. So in this case, we'll take 1 minus 3.5 and square that, add to it 2 minus 3.5, that squared, and then add 3 minus 3.5 squared, and so on until we get to 6 minus 3.5 all squared. But instead of dividing by n minus 1, we now divide by just n. So here what we would wind up with is 35 by 12, which is about 2.92. So that's what we would get for a population variance. Okay, and then we can also talk a bit more about probability. So here I'm going to go and walk through some various kind of situations you could get with probability. So a lot of different examples, some different kinds of events, and such like that. So fundamentally, probability is dealing with events. So these are, like with that dice throw, it could be anything that you're really interested in. So you could look at the event where the outcome of the throw is a 4. You could look at the outcome where the throw is an odd number, a prime number, at most 2, anything really that you could think of. And for any event, it has a probability, and for probability I'm going to use this, this special P to denote probability of an event. For any event you pick, the probability is always between 0 and 1. And when we're talking about some event, the complement of that event is denoted by E with a C as a superscript. And one thing that we can observe is that the probability of an event plus the probability of its complement is always 1. So imagine that our event was that the probability of a dice roll is 4. The complement is everything else that could occur. So for us, for a dice throw, it would be EC would be the event that the dice throw is a 1, a 2, a 3, a 5, or a 6. And we take the probability that the dice throw is a 4, and we add to it the probability that the dice throw is not a 4, we get everything. And when you get all possible outcomes for your sample space, that'll have probability 1. In contrast, if you said something that couldn't happen, so maybe you picked the probability, maybe you were interested in the probability that your dice throw is an 8. So again, standard six-sided die, probability that the dice throw gives you an 8. Well, it's not possible, so that probability is going to be 0. Okay, so one way that we could think about probabilities is with Venn diagrams, especially when we start looking at multiple events kind of stuck together. So suppose that we're going to flip 2 coins. Our first event, A, is going to be the event that we get ahead on the first coin flip, and B is going to be the event that we get ahead on the second coin flip. We can talk about what happens if A and B will both occur. So in this case, that would be getting ahead on flip 1 and then getting ahead on flip 2. And to talk about this, we use this upside down U. So you could think about it as it's kind of an A where it's missing the crossbar. So we're saying the event A and the event B both occur. So in this case, getting ahead on 2 consecutive coin flips. And then the complement of that event is going to be the event that we don't get ahead on both coin flip 1 and coin flip 2. There's a special law that relates these kind of events together, and it's what's referred to as De Morgan's laws. So I just mentioned that this upside down U is effectively denoting an and, so A and B. This right side up U is denoting a union, so an or. So in this case, the complement of A and B occurring is that either A complement occurs or B complement occurs. Both could also occur. That's completely acceptable. And then the complement of A or B occurring is that both A complement and B complement must occur. So in the context of what we just said, A is going to be the event of flipping ahead on toss 1, B is going to be the event of flipping ahead on toss 2. We want to look at what is the probability of A and B, and then also the probability of A or B. So we can think about it with this Venn diagram. So A and B is going to be this purple region. So we have that A is the red region, blue is, or B is the blue region, and then something that's going to occur, or something where we have both A and B, is going to be where they intersect, so this purple region. And for us, for this example, that'll be where both A and B occur, so flipping ahead on 2 consecutive tosses. Now what about the probability of A or B? Well, for that, we're just looking at everything that is in A or in B. So we get this red region, we get this blue region, and then we also get this purple region. So effectively anything that is not in this white area inside the frame. Okay, so one rule that we have for finding the probability of an event A or B is that it's the probability of A plus the probability of B minus the probability of both A and B. And the reason for this is kind of clear from the picture. So we could think about what's going on as the areas of our regions here. So we could say that the probability of A or B we could look at as the combined area from the circle A and the circle B. But if we just add up the two areas, we're going to count a little bit too much. Because when we take the area from A and the area from B, we're going to count this purple region twice. So that's why we're going to need to subtract it off once. So we'd say we're going to take the area from the circle A, we'll take the area from the circle B, and then we'll subtract off the area in this purple region once. So that way we get exactly the area of A plus the area of B, and nothing is counted twice. So we could go about answering this question. So one way that we could look at it is we could just go and enumerate out all of the possible outcomes. So on 2 coin tosses, we'll assume that the probability of getting a head and the probability of getting tails 50-50 for both, so both outcomes are equally likely. There are 4 possible outcomes. We get a head on both throws, we get a head then a tail, we get a tail then a head, and finally we get a tail and a tail. So all 4 of those outcomes are equally likely. If A or B occurs, that means we got either a head on tail 1 or we got a head on tail 2 or possibly both. That's also acceptable because that means both A and B occurred. And in this case, we have that there are 3 outcomes that give us that. So we have a head on both throws, head on the first throw, head on the second throw. So what that says is there are 3 outcomes where A or B occurred, and the total number of possible outcomes that we could have had is 4. So we'll say that the total number of outcomes for A or B, we'll denote it with this hashtag. So that's 3. And then the total number of outcomes that we could have had is 4. So we had 3 outcomes that gave us A or B occurring. We had 4 total possible outcomes, so we'd say that the probability of A or B is 3/4. So in other words, what we're saying is that if you flipped a coin twice, you would expect to get, or 3/4 of the time, you would get a heads if you did this experiment a lot of times. Okay, so the coin flip gives us specific kinds of events known as independent events. So we'd say events are independent if the occurrence of one is independent of the occurrence of the other. So in this case, we're going to flip a coin twice. Regardless of what happens with the first coin flip, that's not going to influence what's going to happen on the second coin flip. And in the event that you have two events that are independent, the probability that they both occur is the probability of the first event times the probability of the second event. We could also talk about mutually exclusive events, and these are events that cannot both occur simultaneously. So suppose that we said we were going to flip a coin once. A is the event that we get a head on that coin flip. B is the B is the event that we get a tails on that coin flip. Well, you can't flip a coin and get a head and a tail simultaneously. So A and B are what we would refer to as mutually exclusive. And the probability of A and B both occurring is 0. One thing that we could also note is that we've just said that the probability of flipping two coins is an independent event. So the probability of getting a head on both toss 1 and toss 2 would be the probability of A times the probability of B, which would be 1/4. So if we used this bottom formula to go and get the probability of A or B, what we would see is that the probability of A is 1/2. The probability of B is 1/2. We add those two numbers together, we get 1. We subtract off the probability of A and B, which we just said was 1/4, and that would give us that the probability of A or B is 3/4, which is exactly what we just had here. And we could have also found the probability of A and B just by enumerating out these possibilities. In this case, the only outcome that we would be interested in that would give us A and B both occurring is that head on the first, head on the second. So there's one outcome of our sample that gives A and B, and there are 4 possible outcomes that you could get from your sample, so the probability of A and B, as we just said, is 1/4. Okay, then we could also go and do some examples with a deck of cards. So let's suppose that we just take 3 cards out of a standard playing deck. So we'll take a jack, a queen, and a king. We'll shuffle the deck, we'll draw 1 card out of that set of 3, we'll observe the result, and we'll put it back into our set of 3 and we'll draw a second card. So in other words, what we're doing is we are drawing with replacement because whatever we draw out, we put back in for the next draw. So there's always 3 things to draw from. So suppose that we take A to be the event of drawing 2 kings. What is the probability of A? And B is the event of drawing 1 king and 1 queen. What is the probability of B? Well, we can observe that as with coin flips, we're effectively doing 2 independent things here. So for A, we could think about A as it is 2 events going on. So the first one is drawing a king on the first card, and the second event, A2, is drawing a king on the second card. And these are the 2 independent events. So in other words, the probability of A occurring is the same as the probability that A1 and A2 both occur. So we draw a king on the first card, we draw a king on the second card. And because those are independent events, the probability of A is just going to be the probability of A1 times the probability of A2. And because there are 3 cards that we're drawing from, all outcomes are equally likely, the probability that we draw a king from our set of 3 is 1/3 in both. So we multiply 1/3 by 1/3 and we get 1/9. Okay, well, how about event B? So the event of drawing a king and a queen. Well, for the moment, the simplest thing we can do is just enumerate out all of the possible outcomes and see which ones give us what we want. So for this, we see one outcome where we draw a queen on the first card, a king on the second one, and then another event where we draw a king on the first card, a queen on the second one. Those are the only 2 outcomes that give us a king and a queen. There are 9 possible outcomes. I've listed them out here. Jack, 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 Queen, Jack, King, and so on. 2 outcomes for B to occur. So that would tell us that the probability of B occurring is 2 out of 9. Again, the other thing we could see here is for A, that event of drawing 2 kings, there was only 1 event, so we get the 1/9 that we just had from a moment ago. Okay, what about if we tinker with the draw a little bit? So we'll take the same kind of setup. We'll take 3 cards from our playing decks. We'll take our jack, our queen, and our king. Now what we'll do is we'll draw 1 card. We'll observe its result. We'll set that card aside and then draw a second card. And this is what you would call sampling without replacement, because whatever you take out, you're putting aside and not allowing it to be taken again. So we'll again take A to be the event of drawing 2 kings, and we'll take B to be the event of drawing a king and a queen, and we'll ask for the probability of A and the probability of B. Well, the first thing that we could say is, as before, we could try and split up what we're looking at as A1 and A2, drawing a king on the first card, drawing a king on the second card. But now what we have is that A1 and A2 are mutually exclusive. The reason for that is because we're taking that the card we draw first and setting it aside, there is no possible way in which we could draw a card on the first draw and also get a king on the second draw. Because if we draw the king on the first time, we've put it aside and it's not allowed to be picked on the second try. So in this case, the probability of A, or the probability of A1 and A2, is 0. Okay, how about event B? So that event of drawing 1 king and 1 queen. Well, now there are only 6 possible outcomes. The reason for that is that we couldn't draw any one card twice. And for these, each of these outcomes is also equally likely. So here what we'd see is that there are still 2 outcomes that result in us having drawn a king and a queen. So we draw the queen first, then the king, or we draw the king first, then the queen. There are 6 possible outcomes in our sample space: jack queen, jack king, queen jack, queen king, king jack, and king queen. So the probability of B occurring is 2 out of 6. Okay, so some notation that could be useful in simplifying things down a little bit is the factorial. So you might remember from maybe high school algebra or something that n factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. A permutation is the number of ways in which you could order R objects from n objects. So suppose that we have a set of n objects and we want to arrange R of them. The total number of ways you could do it is n times n minus 1 times n minus 2 all the way down to n minus r plus 1. Or in other words, you have n factorial divided by n minus r factorial. And then there are combinations which are just unordered choices. So you have a collection of n objects and you're just going to pick r out with no regard for the order. In that case, the total number of ways you could do that, the total number of ways you could choose r objects from a set of n is n factorial divided by r factorial and n minus r factorial. Okay, so let's reconsider that last example once more. So we said that B was the event of drawing a king and a queen without replacement from our set of 3 cards, from our set of jack, queen, and king. And we wanted to know what the probability of B was. So we could think about this in terms of combinations. What we're doing here is we're going to draw 2 cards from a set of 3. And there are exactly 3 ways that you could do it without caring about order. If you want to care about order, that's okay, but we don't need to because we're only interested in drawing 2 cards and winding up with a king and a queen in our hand. So there's one possible way that B could occur, which is that we take 2 cards and one of the cards is a king, the other one's a queen. Again, we're not caring about order here. And there's 3 total possible outcomes that we could have from drawing 2 cards from our set of 3. So that tells us that the probability of B occurring is 1/3, which is what we just found a moment ago. Okay, so another thing that just kind of as maybe a trivial matter that we could look at with combinations, The way the NHL draft lottery is conducted, they put 14 ping pong balls into a machine. All of the balls are labeled 1 through 14, and then they draw out 4. And there's no concern about order, it's just the numbers on the ball. And what you find is that if you draw 14 or 4 items from a set of 14 without concern for the order, there are exactly 1001 possible combinations. So the way that the draft lottery works is they go and assign to each team based on where they finished in the standings from the year before, a certain number of these combinations. So there's a 1, 2, 3, 4, a 1, 2, 3, 5, 1, 2, 3, 14, 6, 9, 11, 13, and so on. So all of these combinations get allocated to the various teams, and whichever team's 4-ball combination comes up on the first draw of 4 gets the number 1 overall pick. Whichever team's combination comes up on the second draw gets the number 2 pick, assuming that that second draw didn't also belong to the first team, and then draw the 4 balls again for the third overall selection. Okay, so we could also come back to this Venn diagram from a moment ago and use it to talk about what's called conditional probability. So suppose that we're told that we have an x value that is somewhere in B. We might be interested to know what is the probability that that value is also in A. So in other words, we're told it's somewhere in this blue region, we don't know where. What's the probability that's in this purple region? And the formula that we have for this is that if A and B are both events, and the probability of B is non-zero, then the probability that A occurs, given that B has occurred, is the probability of A and B divided by the probability of B. And one thing to keep in mind is that conditional probabilities can kind of be very counterintuitive. Okay, so let's consider the experiment where we're going to toss 2 coins again. First, we'll let our event A be the event that the result of both coin tosses is a head, and B will be the event that at least one of the coin tosses results in a head. And we said from a moment ago that the probability of getting at least 1 head out of 2 coin tosses is 3/4, and we'd like to know what the probability of A given B is. Well, we also said that the probability of A and B, and really in this case the probability of A and B is just the probability that both coin tosses are heads, and we said a moment ago that that probability is 1/4, so the probability that both coin tosses are heads, given that at least one of the coin tosses is a head, is going to be 1/4 divided by 3/4, or 1/3. Another way that you could think about this is that what we're doing is we're restricting the sample space down. So when you toss 2 coins, you could get 2 heads, a head then a tail, tail then a head, or 2 tails. What we're saying now is we're not going to consider the event where, or we're not going to consider the possibility where we get 2 tails. We're just going to look at all of the cases where at least 1 head showed up. And in just looking at those, what is the probability that we get 2 heads? Well, now we only have 3 possible outcomes. 2 heads, head then tails, tails then heads. And we would say that each of those 3 outcomes is equally likely. And one of them gives us a head, 2 of them don't. So the probability that we get a head, or the probability that we get 2 heads, given that we have at least 1 head showing up, is 1/3 just by enumerating out the outcomes. Okay, so here's also an interesting example. So what I have here is a table where I've got 2 airlines, airline A and B, and they fly into 5 various cities across Canada, and we have the percentage that their flights are on time for each of the different airports. What we see at the very bottom is that airline B is on time more often than airline A. But when we look at the individual airports, what we see is that at each place, airline A is more on time than airline B. So for flights into Vancouver, airline A is on time 88.9% of the time, airline B is on time 85.6% of the time. Into Calgary, airline A is on time 83.1% of the time, B is on time 76.7% of the time, and so on. Okay, so why might this be happening? Well, notice that the bulk of Airline B's flights are into Toronto. And that is also where it has the biggest proportion, uh, or that is where it's also got where it's most on time. So they have the overwhelming amount of the flights from Airline B are into Toronto, and um, that's where they have the best on-time performance. Airline A doesn't fly into Toronto as much, but when they do fly into Toronto, they have they still have a better, um, they're on time more often than Airline B. Most of Airline A's flights are into Montreal. Um, they're on time more often than Airline B when flying into Montreal, but as a um, as an average, their flights into Montreal are below their average from the other cities. So Montreal has this disproportionate impact that is dragging down A's performance overall. And that kind of explains why Airline A has a lower overall on-time average, but despite having a better on-time percentage at each of the individual airports. And, so this is kind of a strange result. And one way that you could think about it is you have a lot of conditional probabilities going on. So you'd have the probability that a flight from Airline A is on time, given that it's going into Montreal, um, the probability that a flight from Airline B going into Montreal, or the probability that a flight from Airline B is on time, given that it's going into Montreal, and so on. So you can get some kind of counterintuitive results showing up with conditional probabilities. Okay, and then I thought I'd mention one other kind of interesting, um, also counterintuitive result from probability. So from the course roster, there are 22 of you, and then there's me, so there's 23 of us all together. And we might ask, what is the probability that out of the 23 of us, 2 of us share a birthday? Now, intuitively, you might think this is quite small. There's, we'll say, 365 days in a year. So the likelihood that any 2 people share a birthday, you would think is kind of small. So we'll just exclude February 29th from consideration. And what is our sample space? Well, our sample space is all of the possible enumerations. So all of us, for example, could have been born on January the 1st. All of us could have been born on January the 2nd. One person could be born on January 1st, one person on January 2nd, one person on January 3rd, and so on. So all of the possible outcomes for birthdays. So there are 365 days that any one of us that could have been born on. There are 23 of us. So there are 365 times 365 times 365 and so on, 23 times possible outcomes. So a lot. And we'll let A be the event that at least 2 of us share a birthday. And what we want to find out is, out of these 365 to the 23 possible outcomes, how many of them result in 2 people sharing a birthday? Well, remember from a moment ago that we'd said that if we have 2 events A and B, the probability that either A or B occurs is the probability that A occurs plus the probability that B occurs minus the probability that A and B occur. Now, if you have 3 events, A, B, and C, this expression gets worse. You have that the probability that one of A, B, or C occurs is the probability that A occurs, plus the probability that B occurs, plus the probability that C occurs, minus the probability that A and B occur, minus the probability that A and C occur, minus the probability that B and C occur, plus the probability that all 3 of A, B, and C occur. And the reason for this is very much related to what I'd said about the Venn diagram a moment ago. And you can imagine that if you have 4 events or 5 events, or in our case 23 events, this equation gets very bad very quickly. So finding the probability of A, or finding the number of events that result in A occurring, is not going to be easy here at all. So what can we do? Well, instead of looking at the number of ways in which A could occur, we'll look at the number of ways in which a complement could occur. So remember that we had said that the probability of A plus the probability of a complement is 1, And another way of saying that is that the number of ways in which A could occur plus the number of ways in which a complement could occur is the total number of possible outcomes that you could have. Because if we take any collection of birthdays, well, it's either the case that at least two people share a birthday or it's not. So you take any outcome, you get one of those two possibilities. You take all of the outcomes in which at least two people share a birthday. You take all of the outcomes in which you don't have two people sharing a birthday. That's going to be your total collection of possible outcomes. So a complement is the event that no two people share a birthday. And maybe we can find this a little bit easier. Okay, so what has to happen for a complement to occur? Well, we could think about it as we're going to just look at the sequence of all the people. So we start with person 1. Person 1 could have any of 365 birthdays in the year. Totally acceptable. Now, if a complement is going to occur, so two people aren't going to share a birthday, that means person 2 cannot share a birthday with person 1, or there are 364 possible birthdays for person 2 to have in order for a complement to occur. Okay, so we've now set two birthdays. We've set the birthday for person 1, the birthday for person 2. We then look to person 3. Person 3 can have any of the remaining 363 birthdays that haven't been accounted for. And this keeps going. So we're going to get that the number of ways in which a complement could occur is going to be 365 times 364 times 366, all the way down to 366 minus k. For us, k is 23. So the total number of ways in which no two of us could share a birthday is 365 times 364 times 363 times on and on times 344 times 343. So what that says is we have the total number of ways in which a complement could occur. We know the total number of possibilities is at 365 to the 23. So the probability that a complement occurs is this 365 times 364 all the way down to 343, all divided by 365 to the 23. But remember that we were looking for the probability that at least two of us share a birthday. And if we want to find the probability that at least two of us share a birthday, we just take 1 minus the probability of a complement. And in that case, this probability works out to about 50.73%. So actually, the probability that any two of us share a birthday is over 50%. And 23 is actually, interestingly, the smallest number of people that you need to get the probability of at least two people sharing a birthday over 50%. Okay, so let's come back and talk a bit about random variables. So when we were looking through R the last time, I went and used this example of the heights of NHL players from last season. And what we have is this total table of values. So we have, there's one player that's 5'6", 3 that are 5'7", 191 that are 6'1", one player that is 6'9", and so on. Okay, so the total proportion of players that are 6'1" is about 19%, 191 out of 1,003. So the numbers work kind of nicely here. So we could take x to be the random variable describing the height of a randomly chosen player. So we're going to just put all of the NHL players into a pot. We're going to randomly pick one out, and x is our random variable to describe the height of a player randomly chosen. So we want to find the probability that x is 73, or we would say, if we wanted to talk about an event, we could say let E be the event that a randomly chosen player has height 73 inches. Well, from this, what we said is that there are 191 ways for this event E to occur. There are 191 players that are 6'1", 73 inches tall. There are 1,003 possible players to choose from, and choosing any one player is as likely as choosing any of the others. So the probability that the height of a randomly chosen player is 73 inches, or the probability that E occurs, is just 191 divided by 1,003, or about 19%. Okay, we could also look at different events. So we could say, what is the probability that the height of a randomly chosen player ends in a 0. So is either 70 inches or 80 inches tall. In this case, there are two ways that could occur. We could have one of the 63 players that is 5'10", or we could have the one player who is 6'8" and choose them. And also, we could look at it as we have two events going on here, but the events are mutually exclusive. We can't draw a player that is simultaneously 5'10" and also 6'8". So in this case, there are 64 ways that you could draw a player who has height that ends in a 0. So we would get about 6.38%. Okay, how about the event where a randomly drawn player has height less than or equal to 90 inches? Well, in that case, that probability is going to be 1 because all of the players are less than 7'6". Okay, so that one's easy. How about the probability that we get a player that has height that is less than 65 inches or bigger than 82 inches? Well, there the probability is going to be 0 because there is no player that is 5'5" or shorter or 6'10" or taller. So there are no ways that that can be achieved. So we wind up with a probability of 0. Okay, and then the other thing that we could do from this is we could calculate the population mean and the population variance. And if we did that, what we'd see is that the population variance, or sorry, the population mean is about 73.14 inches, and the population variance is about 4.54 inches. And these ideas of population mean and population variance lead us to what is called the expected value and the variance for a random variable. So for a random variable that we're going to draw from a population where all of our points are y1, y2, all the way up to yn. So thinking about this from the example we just had, we'd have 1,003 points. Each of the yj terms would be the height of one of the players. So x, again thinking about it in terms of the previous example, x was the height of a randomly drawn player. The expected value for this random variable is just the population mean. So we would take 1 over n and sum up all of the values in the population. So we would take, we'd have 166, we would have 367s, we would have 1068s, and so on. We'd sum up all of those values, we'd take the average, that would be the expected value for our random variable. Another way that we could put it is we could look at just the probability of each of the distinct values. So we could look at the probability of 66 showing up, the probability of 67 showing up, probability of 68 showing up, and so on. And we could say, we'll take the sum of 66 times the probability of getting a 66, so 1 in 1,003. Then we could add to it 67 times the probability of getting a 67, which was 3 in 1,003, and so on. Similarly, we can calculate the variance for our random variable. So we could calculate the variance just as we would the population variance. So we'll take 1 over n times that sum from j equals 1 to n of each of the y values minus the expected value, and take that all squared. Or we could take the sum over all of the distinct values. So we would take 66 minus the expected value of our random variable. So we said about 73.14. Multiplied by the probability of getting a 66, and then add to it 67 minus the expected value times the probability of getting a 67. Take a 68 minus the expected value, square that quantity, multiply by the probability of getting a 66, take that sum. You'll get the exact same thing in both cases, just different ways of writing it. The second one for both of these using the probability just kind of collapses down the number of operations you need to do. So for this, you would need to do 1,003 additions. For this one, so it collapses down the number of operations that you need to do if we were to use the first one here, where we'd be looking at the sum of all of the values in the population, you'd have to add up 1,003 values. For the second one, you just need to add up 16 values times some probabilities, so it simplifies the calculation a lot. Okay, and then the last thing that I want to do before getting into R is going and looking at, instead of throwing one die, looking at what happens when we throw two die. And this also nicely relates to one of the homework questions where you get to go and look at what happens when you throw three die. So what we're going to do here is we're going to let x be the random variable describing the sum of two dice thrown. And for the homework, you get to look at what happens when you throw three die and sum up the values from those three die. Okay, so what I've done here with this table on the top is I've just listed out all of the possibilities. So along the top we have the values from the second die, and the column here is going to give us the values from the first die. So we have a 1 and a 1, that adds up to 2. We could get 6 from both of our dies, and that gives us a sum of 12. Okay, so what is the probability that we throw 2 die and we get a sum of 7? Well, the probability there is going to be 6 out of 36, so we have 36 total values, and we see that there are 6 sevens, so 1 in 6. And this kind of makes sense because regardless of what you throw on the first die, you can always get a 7 by throwing the appropriate number. Now, if we asked, what is the probability of getting an 8? If you throw a 1 on the first die, there is no possible way that you could get an 8 on, get your 2 die to sum up to 8. So it makes sense that we only see that there are 5 ways of getting an 8. So we could also look at the event where the sum of our 2 die is a prime number. So to do that, we would go and add up the probability that x is 2, the probability that x is 3, the probability that x is 5, the probability that x is 7, and the probability that x is 11. And if we add up all of the 2s, 3s, 5s, 7s, and 11s that we see here, what we see is that there are 15 of them. So there are 15 ways in which you could throw 2 die, add up the result of those 2 die, and get a prime number. Okay, now what I'm going to do is I'm going to go open up R, and I'm going to go and show you some ways that you could go and do this on your own. Okay, so in this one, I'm just going to go and pull up a little bit about random variables, show you that things all kind of work out nicely. There's one small error that I made because I copied down the wrong number, so I'll just correct that here kind of quickly. And then set you up nicely so that you can go and do everything you need for the homework. Okay, so the first thing that I'm going to do is go and pull that players file from last time back into memory. The average for the height is about a bit over 73 inches, and the variance is about 4.54, and this is where I made the small mistake because I copied down the wrong number. Okay, and then I'm going to go and put all of the variables, or all of the values from that height vector into this variable x, and I'll do some stuff with it momentarily. And I'm also going to go and define a value, a variable expected value, and that'll just be that the average value for the heights. Okay, so this expression is the population variance. So what we said for population variance is that it looks like the sample variance. The difference is we divide by the total number of entries, not the total number of entries minus 1. So what's going to happen here is we're going to take each value in x, just to make sure that we've got what we want. We have head x, so those are our first 6 values in x. So we're going to go through each value in x, we're going to subtract off the expected value, we're going to square that result, and then we're going to divide by the total number of entries in the end. So we're going to take 74, subtract off this 73.14, whatever, square it, divide by 1003. And when we do that, we get about 4.53, which is different than the value we get up here, and the reason for that is because when I call the variance there, it is taking the length minus 1. So here it's taking this part, but dividing it by 1002 instead of 1003. So minor correction. Okay, then the second thing that we're going to do is we're going to look at some dice rolls. So the first thing I'm going to do is just define a variable that's going to have 6 entries for the 6 faces on a standard die. And then I'm going to create a new vector called sample space, and I'm going to go and put all of the values from my sample space into that vector. So what this is going to do is it's going to go and effectively loop through all of the possible outcomes. So I could get a 1 on the first die and then any of 1 through 6 on the second die. I could get a 2 on the first die and any of 1 through 6 on the second one, and so on. And then what this is going to do is this is going to take all of the entries that are in sample space and it's going to add the next sum to the end. So first I'm going to have 0 values in my sample space. My first value for J, my first value for K will be 1 for both of those. So I'll get an empty list and then I'll get 1 plus 1. So my first entry should be 2. My next entry will be 3 and so on. Okay, so what does sample space look like? All right, so we get sample space is kind of as I said. For the first values, we get J is 1, K is 1, then K is 2, K is 3, K is 4, K is 5, K is 6. We add a 1 to all of those. Then J is 2, K is 1, K is 2, K is 3, K is 4, K is 5, K is 6, and so on. Okay, and then I'm going to do the same thing as above. I'm going to put into X all of my sample space. So effectively what I'm doing is I'm saying, this is the population that I'm drawing X from. And let's go and find some probabilities for our random variable X. Okay, so this looks kind of strange. I'm saying mean of X equals 7. Well, I said a couple of minutes ago that the probability that your random variable X that is describing the sum of throwing a pair of die is 1/6, which is 0.166 repeating, which is what we have here. So we get the correct answer, but it's maybe not clear what R is doing. So if we just look at X equals 7, we get this vector of true and false values. So the first value is false, the second is false, the third is false, the fourth is false, the fifth is false, but the sixth is true. And what that's doing is it's saying, this is not 7, that's not 7, that's not 7, that's not 7, that's not 7, but this one is 7. So every value in here that is 7, we're getting a true in that position, and we get a false in all the others. And then when it's going and evaluating the mean, it is going and summing up the value of this vector, where it's assigning 1 to each true entry and 0 to each false entry. So there are 6 trues, 1, 2, 3, 4, 5, and 6. And the rest are false, so we have 36 total entries, 6 are true, so the mean is going to be 6 out of 36 in this case, so 1/6, as we'd said before. Okay, well, how about X equals 8? We'd said that there are 5 total ways in which you could throw 2 die and get a sum of 8. And when we call the mean of X equals 8, we get 5 out of 36. If you wanted to go and look for the probability that your random, that you throw 2 die, you sum them up, and you get a prime number, we could do this. So we're going to take the mean of X is 2, or X is 3, or X is 5, or X is 7, or X is 11. So in R, if you want to do an OR between conditions, so I have here X is 2 or X is 3, I use this vertical bar symbol, so just below the delete key. So with this one, we'd said that we would get 15 out of 36, which is exactly what we get here. So maybe we want to do an AND, so X is bigger than or equal to 6, and X is less than or equal to 8. So this would be X is either 6, 7, or 8, and we get a 4 repeating. The total number of ways you could do that would be 16 by 36, which is 0.4 repeating. Okay, and then We could also just do something like find the mean for x values less than or equal to 4. There you would get one possibility is 2, two possibilities of 3, three possibilities of 4, so 6 out of 36 again. Okay, so then we could also just go and do some sampling. So what I'm going to do is I'm going to define two variables, dice1 and dice2. So what this is going to do is it's going to take all of my possible outcomes of throwing a die, sample it 10,000 times, and do it twice. So in dice1, what I'm doing is it's the equivalent of saying I'm going to throw my first die 10,000 times and record all of those outcomes. Then in dice 2, I'm going to throw my second die 10,000 times, record all of those outcomes. And again, you want to keep the replace equals true, because if you don't, this won't work. Now what I'm going to do is I'm going to make a new variable that is dice sum. It's going to be dice 1 plus dice 2. So what that's going to do is it's going to do an entry-wise sum, and I'll just, let's call head of dice 1, head of dice 2, and head of dice sum. Okay, so notice that dice 1, these are the first 6 values, 6, 1, 4, 5, 6, and 2. And the first 6 values in dice 2 are 5, 1, 1, 3, 6, 5. And what dice sum is doing is it's saying, I'm going to go to the first entry in each, add them up. So I get 6 plus 5, I get 11. Then we go to the second entry, we get 1 plus 1 for 2. We go to the third entries, which is 4 plus 1 for this 5. Then 5 plus 3 for 8, 6 plus 6 for 12, 2 plus 5 for 7, and so on. Okay, so then what we could do is we could call a histogram for these results and see what we wind up with. All right, so we wind up with this this nice plot, and this gives us something that we'd kind of expect. The values look very symmetric. So the most common value is 7. We get 6 showing up about as often as 8. We get 5 showing up a little bit more often than 9. 4 showing up a little bit less often than 10. Looks like 3 shows up about as often as 11, and 2 shows up about as often as 12. Okay, so that tells us a little bit about how we can use R to go and help us out with some random variable stuff, and I think this gives you all of the tools you need to go and deal with the homework. If you have any questions, let me know, and I will see you in the next video.